Hello friends, welcome back to the tetrahedron chemistry classes. Guys, in today's lecture I am going to solve another 11 problems from the CSIR NET 2013 examinations. And previously I have solved the questions from the 2011 and the 2012 CSIR NET question papers. Okay, in this lecture series, my first question is, you can see here what the question says. It says, in the NMR spectroscopy, the product of the nuclear G factor, that is Gn, and the nuclear magneton, that is beta n, and the magnetic field strength. That means if you multiply all these three, what it will give you? Whether it will give you the energy of the transition from alpha to the beta state, or it will give you the chemical shift, or it will give you the spin-spin coupling constant, and it will give you the gyromagnetic ratio or magnetogyric ratio. Okay, so this question is quite simple. If you have studied the basic theory of the NMR spectroscopy, then there is no problem in solving such kind of the problem. So if you start from here, actually from the chemical shift, you know what is the chemical shift on the delta scale, that is delta ppm. It is nothing but shifts in hertz, okay, divided by spectrophotometer frequency. Spectrophotometer frequency, and that is in megahertz. Okay, so in that case, you can see in case of the chemical shift, neither Bn nor actually Gn is involved here, so this B cannot be your answer. Okay, and in the similar note, if you see the coupling constant, that is the J value. So you know what is the J value. If you have the splitted peaks like that, and if you measure the distance between the splitted peaks in the hertz, that will give you the value of the J. So this J is again not related with your term beta n or the Gn. So this you can also exclude from here, right? Then you left with the gyromagnetic ratio or magnetogyric ratio, which is generally shown by the gamma. And I hope you know what is gamma and how we can calculate. Basically, it's an experimental value. It is an experimental parameter, and we can calculate actually experimentally this thing. And this actually shows the sensitivity of the nuclei towards the NMR spectrophotometer, and it is not related to the beta n and the your Gn. So this can also be discarded. So if you know the basic theory, then obviously you can discard option B, C and D, and what you left with the option C. So option C is the correct answer. And if you want to know the little more something about this, so you should know actually only this relationship actually, right? You see, if you want to calculate the energy of the nuclei in any magnetic field, so you can write energy of the nuclei, right, in the magnetic field, that is Mi, this is quantum number, and that is equals to negative of Gn, which is your this value, or you can write capital N also. So I can write capital N, that is the Gn, nuclear G factor, and this nuclear G factor is combined with your magnetic moment of the nuclei, that is nu n, multiplied by the B0, right, and Mi. So there is no need to solve this question further, because all these parameters actually is giving the energy of the nuclei in the magnetic field, and you know the energy of the nuclei in any magnetic field can be given by what? Delta E. Okay, and that delta E is what? Energy of the nuclei in the beta spin state minus energy of the nuclei in the alpha spin state. So if you want to determine the distance between difference of these two, so you can write minus of Gn mu n B0, and for M, since it is the beta state, you are calculating for the beta state, and for beta state this value of the Mi is minus half. So what you can do, you can write minus half here, minus 1 by 2, and then you can enclose this, then minus, since you are getting you are calculating the difference, so this is minus, this is also minus here, and again you can start this bracket here. So minus is already there in that in this particular formula, so you can write minus G of n mu n B0, that is the magnetic field, and then the value of Mi for the alpha state, and for alpha state the value is what? Plus half. So you can write plus half here. Okay, and if you solve this little further, like that, So this will give you delta E equals to Gn mu n B naught. Mathematically these terms will get cancelled out, and after final solution you will get this thing. Okay, so what it is giving you, it is actually giving you the difference between the alpha and the beta scale. Okay, so this is the energy of the transition from alpha to beta. Only this option is given. However, I have calculated in that manner that E beta is having higher energy and E alpha is having lower energy, so I have calculated this difference. But you can remember this formula to solve such kind of the problem. So this is the basic problem, nothing special in that. Okay, now moving to the next problem, what it says. Okay, my next problem, as you can see here, in the IR spectrum, the absorption band due to the carbonyl in phenyl acetate appears at, okay, you have been given 4 options, and the question is asking about the carbonyl stretching frequency for the phenyl acetate. So it's a, see guys, again it's a memory based question. If you have memorized the absorption frequencies of the carbonyls, then it is very easy for you to actually solve such kind of the problem. So to solve this, first of all you have to draw the structure of your phenyl acetate, which is given in the question. So for phenyl acetate, what you can do, you can write your benzene ring just like that, and it is connected with the oxygen here, and this is your OCH3. So this is your phenyl acetate. How you can understand it is phenyl acetate? Say this is your acetic acid. Replace this hydrogen with the C6H5. Then you will have your CH3, COO, C6H5. That is what I have written here. C6H5 connected with the oxygen, and this is the methyl group. Okay, and you know this oxygen is having the 2 lone pairs over there, and these 2 lone pairs actually are delocalized onto this benzene ring. So resonance goes in that manner. So if you draw like that, you know this is, then it will become your electron withdrawing group. That means it will suck the electron density towards itself, and you know this a methyl group, any alkyl group is actually a electron pumping group. So it is actually electron donating group. And how it donates the electrons? Due to plus I effect. So what happens, you can see guys here, when the electrons this methyl group pumps the electrons towards this carbonyl, so electron density gets increased here, right? And this increased electron density will be sucked by the oxygen, right? And in that case the polarity will increase, the polarity of carbonyl group will increase, right? And due to this the bond will become stronger, and bond will become stronger, then this carbonyl frequency will shift towards the higher side actually. And but to solve such kind of the problem, you should know your esters, when you have the normal esters, okay, without any conjugation, then they have the carbonyl frequency range between 1700 and 35 to 1750 centimeter inverse. Okay, this is without conjugation. But in that case, you see this conjugation actually, this is electron withdrawing group, right? And this is pushing the electron here, electron density towards this carbonyl, which is making this bond somewhat stronger. When the bond becomes stronger, that means obviously you will require the higher energy to stretch this particular bond, and higher energy will require. Higher energy reflects in the higher frequency. So definitely this carbonyl frequency range for this carbonyl group for this particular molecule should be little higher than your 1750, right? And exactly it is it is found somewhere in the range which is a little bit on the higher side. Okay, so when it is in the higher side, so how you can exclude the certain problems? You can exclude this 1710, you can exclude this, right? Even you can exclude 1800. So 1760 is looking good in that case. So this option B actually in that case is looking the correct answer. Okay, so this is how you can solve. But again, please remember these questions are the memory based question, and you have to memorize the things before you solving such kind of such kind of the problems. Now moving to the next problem, what it says. Okay, now this is my another problem. What it says, you can see here, an AX systems gave the 4 lines at this and this, these values. They have been given the 4 chemical shift values away from the TMS, and in that case you have been also given the strength of the spectrophotometer, which is of 100 megahertz. So you have to calculate the coupling constant and the chemical shift. Okay, so this is first of all, you see such kind of the problem I have already solved in my previous 2 lectures actually, right now. But if you want to solve, if you want to know a little more insight about such kind of the system, then you should know this is the AX system. If it is the AX system, this is actually the active nuclei, NMR active nuclei, and this X is also the NMR active nuclei. Okay, so what will happen when both the nuclei are active? So the signal of this A would be splitted by this X, and the signal of the X would be splitted by the A. So that means both will split each other's signal. Okay, so if you calculate for A actually, okay, if you calculate for A, so you will get a doublet for A, just like that. Okay, because this singlet is actually splitted by the X. Now if you move little bit further like that, if you want to know the signal of this X, right, so again it would be splitted in this doublet. Okay, and this doublet is due to the A in that case, right? And since you have been given the values here, so the trick is that whatever the chemical shifts are given in the question, you will start from the right hand side, because it is 1.0 here. Somewhere here you will have the 0.0 ppm, which is the signal of the TMS, right? And away from the TMS at 1 ppm you are having this signal, and 1.12 ppm you are having another one, and then little bit higher side downfield signal, that is 4.6 and 4.72. These values are given in the question itself, guys. You can see here it gives the doublet of the doublet, right? Doublet for this and doublet for this, so it's a these are the 2 doublets actually, right? And in this doublet you see 1.0 is the chemical shift, which is for this one, 1.12 for this one, 4.6 for this one, and 4.72 for this one. Okay, now in that case what you can see, you can take the average, right? So how you can take the average? So for average, say for example I am calculating for this one, see I want to look, or I am looking for the center of this. So how you can determine the center? So I am taking the average for this one, which is what, 4.72 plus 4.6 divided by 2. If you solve this, then it will give you 4.66 ppm. So here at the center you are having 4.66 ppm. There is no problem in that. And again, if you want to know the center of this, so again you will take the average of this one. So how you will take the average? 1.12 plus 1.0 divided by 2. If you solve this, it will give you 1.06. So this center is actually 1.06 ppm. Okay, and now you have to calculate the chemical shift of this. So what is the chemical shift? You see here, chemical shift is what? From here to here, from this center to this center, right? This is what your delta AX. You can take in that manner. See, however, there are other ways also by which you can calculate, but I am taking this particular example. So how you can take the delta AX? So delta AX would be equal to what? 4.66, which is the center of this. You see here, 4.66 minus 1.06. So again you will subtract this here, minus 1.06. This will give you 3.6 ppm. So chemical shift 3.6 ppm is given here. So now you can check the options here. This is 3.6, so this could be the answer. This is also the 3.6, this could be the answer, but it is 2.86, this cannot be your answer. This is again 2.86, this cannot be your answer. So immediately you can strike out the 2 options. Now what you can do, you can calculate now the coupling constant. So what is the coupling constant? I have already told you the distance between the splitted peaks. So the distance between these two, or the distance between these two, or some other method you can apply to calculate the J value. So how I can solve this? Say I am calculating the JAX. So for JAX, what will you do? You will write 4.72 minus 4.6. How I have taken this one? See, this is 4.72, this one, and this is 4.6. So what you can take the distance between these two. Distance between the splitted peaks in hertz, when multiplied by the spectrophotometer frequency, it will give you the value in the megahertz. Okay, so or in hertz it is simply the difference between these two. Okay, so if you take the distance of these two, difference of these two, so this will give you 0.12. Okay, and similar result you can find in another way also. Say for example, you can take the difference of these two also. So how you can take 1.12 minus 1.0, it will give you 0.12 in both ways, right? Whether you take the difference of these two, whether you take the difference of these two, they both will give you the same result. Okay, now what I can do, I can solve now further this delta ppm, that is the chemical shift. Okay, this is equal to difference in hertz divided by spectrophotometer frequency. This is the formula of the chemical shift. Spectrophotometer frequency. Okay, so in that case this delta ppm I have already calculated. Okay, this delta ppm this I have already calculated, and spectrophotometer frequency I have also this is also given actually in that case. So what you can do, you can simply give this take this value 0.12. Okay, and when you multiply this with the spectrophotometer frequency, right, this difference in hertz you are calculating, sorry. Okay, so this will give you 0.012 multiplied by 100, that is give you the 12 hertz. Okay, so this 12 hertz is there in this option A. So option A is looking the correct answer. So if you do not want to apply this particular formula, then you can forget about this, but you can simply, what you can do, whatever you have got here, distance between the splitted peak, when you multiply this value with the spectrophotometer frequency, you will get the result. So this is how you can solve this problem also. Okay, now moving to the next problem, what it says. Okay, this problem says among the following, the correct statements for the following reaction is. Okay, so guys, this problem actually is looking like the looking like that it is a very complex problem, but actually it is not a complex problem. It's a very simple problem, and you do not need to worry about the mechanism of the reaction and the product. They are all, see in the question itself. If you see here what the question says, this is the 7-membered ring and its ketone is here, and it is simply reacting with the Grignard reagent followed by the acidification, and it gets converted into the these two products A and B. And you know, if you know the basic general organic chemistry, basic organic chemistry, this A is actually the most this is the major product. Why major product? Because this alkene is the more substituted alkene. Right, see, this is double bond here, this is your alpha carbon which is having the 3 hydrogen, and this alpha hydrogen which is having the 2 hydrogens. Similarly 2 hydrogens are here. So for this you are having 3 to 5 and 5 and to 7 hyperconjugative structure. So basically it's a ZF product in any these kind of the reaction, right? When the formation of the alkene occurs, right, and you have a product which is the more substituted alkene, it is the more stable one, right? And this alkene is the less substituted because only 2 hydrogens are here on this alpha carbon, 2 hydrogens are there on this alpha carbons, that means only 4 hyperconjugative structures are there. So this alkene is the less stable alkene, and since it is the less stable alkene, you can write it as the minor product. Okay, and now check what the option says. Here it says you can check here, A is the major product. Of course A is the major product, there is no problem. A is the minor product, no, and A cannot be the minor product, so B is not your answer. Now moving to the next one, B is the major product, and here you see the B is the minor product, so this C can also be not your answer, so you can strike out B also. Now third you left with what? B is the minor product. Okay, fine, B is the minor product, A is the major product. So now you have to select between A and B, because both the statements about the majority and the minority of the product is correct in that case. Now you have to look for the number of the NMR signals. In that case, you have to look for the NMR signals. How many NMR signals the particular compound will give you. So what you can do, say what I can do, if you check this particular compound, so this is the plane of symmetry which is passing through this center. This is the plane of symmetry, right? This is the plane of symmetry, and you can write it as the sigma plane. It is the sigma plane, and whenever the sigma plane is there, that means the reflecting carbons are the same kind of the carbon. That means this carbon is reflecting here, that means these two are same. So what I can do, I can give them number. This is carbon number 1, this is carbon number 2. Now moving to the next one, this is carbon which is reflecting here, or I made a mistake actually. I can write it as 1. Okay, why 1? Because this is 1 reflecting here due to this symmetry plane, so both are same. Now moving to next one, say this is carbon number 2 which is reflecting here, so these two are same, so I can write 2 for these two carbon, 2 and 2. Similarly, this is carbon 3 and this is carbon 3. That means compound B will give you the 3 signals in the carbon NMR spectrum. This will give you the 3 signal. So now you can check here, A is the major product, fine, there is no problem is that, and it will have the 5 signals. So A will give you the 5 signals. So let me check whether it is giving you the 5 signals or not, right? But unfortunately it will not give you the 5 signals. Why it will not give you the 5 signals? If you number the carbon atoms here, say this is carbon number 1, this is carbon number 2, this is 3, this is 4, this is 5, this is 6, this is 7, this is 8. So this compound, that means option A, this will give you the 8 signals in the NMR spectrum, 8 signals. So A is the major product, very fine. It will give the 5 signals. No, it will give you the 8 signals. So this cannot be your answer. So what you left with the option D. D is the minor product and it will have the 5 signals in the proton decoupled 13C NMR spectrum. Now we can check how it will give you the 5 signals. Okay, so it's quite easy, guys. You see here, this is carbon 1 signal due to this one signal due to this one, and 1 signal due to this one. That means 3 signals are there, and 4 signal for this CH2 and the 5th signal for this CH2. So if I draw it again just like that, okay, and say I am putting a double bond here. So this is carbon number 1, this is carbon number 2, and the symmetry plane is here. Okay, so this will give you 3, this will give you 4, this will give you 5. So I haven't drawn, I didn't draw the correctly, but you can understand the problem in that manner. So option C actually is looking the more correct option in that case. Okay, so now we can go for the third problem. Next problem. Okay, what it says, in the UV visible spectrum, a diterpenoid exhibited a lambda max at 275 nanometer. The compound among the following choices given below. Okay, this problem is based on the Woodward-Pfizer rule. Okay, and you can calculate the lambda max for this one. And these are the diterpenoids. You can calculate the number of the isoprene units here. I have already made a video how to decide whether it is a diterpenoid, monoterpenoid, or a sesquiterpenoid or tetraterpenoid. Right, I have given you a trick also, and in the description box I am giving you the link of that video also, so that it would be very easy to understand how to decide which is the monoterpenoid, which is the diterpenoid, okay, and other terpenoids also. But I am going to solve this particular problem, how we can solve this one. For this you have to memorize the Woodward-Pfizer rule. Okay, so for this I am solving this one. So this is the diene system. If you follow, this is the diene system, and this diene system is the transdiene system, because this double bond is here and this double bond is here. Okay, this is the transoid one, and for transdiene the base value is 217. Okay, the base value, so I can write here parent value, which is 217. Okay, right, and of course it is in nanometer, so I will not write nanometer again and again. So this is 217 nanometer. Now you can calculate the ring residues. So this is the ring residue number 1, this is ring residue number 2, this is ring residue number 3. So 3 ring residues are there. So you can write 3 into 5 that will give you the 15. Okay, so 3 into 5, 15, and then you can calculate this. You can see this, this is alkyl substitution. So one alkyl substitution is there, so you will add the 5, further 5. So 5, what you are having? You are having 217, you are having 15, you are having 5. Now you can go for the exocyclic double bonds. Okay, so you see this is the ring A, this is the ring B, and this is the junction, and this double bond is here. So this double bond is exocyclic to this ring. So one exocyclic double bond is there, and for one exocyclic double bond we always add the increment of the 5 nanometers. So you will add 5 here. So this is the final result. So if you add all of them, 15 plus 5, 15, see 5, 5, 10, 10, 5, 15, 15 and 7, 22, 22 or 3, 4 and 2, 242 is the answer. But in the question itself you can see what is given here, 275. So this is not the correct answer. You can strike out this. So guys, if you find little bit difficult to solve this problem, you can go to my channel and you can search the UV visible spectroscopy, or you can write the Woodward-Pfizer rule by tetrahedron chemistry classes. So I have solved the large number of the problem based on these rules there. Okay, now I am going for this one, the second problem. This second problem, you can see this double bond is here, this is single, this is double, so it is not a diene system. When it is not a diene system, you cannot apply the Woodward-Pfizer rule on this particular molecule. So this B can also be not your answer. So you can strike out B also. Now moving to the third problem, which is this one. Okay, now this is your diene system, and this diene is the cis diene. Okay, so for parent diene system, you will write 217 nanometer. Okay, and since this is the cissoid or the cis diene system, or you can say the homoannular diene. So for homoannular diene, you will add 36 nanometer to it. So you can write 36 nanometer. Now you can go for the ring residue. So this is the ring residue number 1, this is the ring residue number 2, this is the ring residue number 3. So 3 ring residues are there. Okay, and for 1 ring residue you will add 5, for 3 you will add 15 nanometer. So you will add 15 nanometer here. Now you can go for look for another thing, that is the alkyl substituent. So this is the alkyl substituent, which is 1, and for 1 alkyl substituent you always add 5 nanometers. So we will write 5 here. And now you can look for the exocyclic double bond. So for exocyclic double bond, you see this is the ring, this is another ring, and this is the junction, and this double bond is present at this particular junction. That means this double bond is exocyclic to this particular ring. And for 1 exocyclic double bond, you add the 5 nanometer increment further. So what you can do, we will write 5 here. Now you can add all of them. 15 plus 6, 21, 21 plus 7, that is 28. Okay, 28, that is 2, 3, 6 and 7, and 278. So your answer is 278, and this 278 actually is quite close to 275. This option C is looking the correct answer. Remember, in Woodward-Pfizer rule, the error of plus minus 5 nanometer is allowed. So this is looking the more correct answer. If you want, then you can check for this one also, right? But this is the trans diene system, right? So if it is a trans diene system, for this the base value will always be your 217. Okay. And after 217 you will add the ring residues, that is 1, ring residue 2, ring residue 3. Okay, so if you add 3 in that case, that means 15. Now you can go for the alkyl group. This is one alkyl group, this is another, that means 10 you will add further. And this double bond is exocyclic to this, so you will add 5 here. Okay, and if you add all of them, 5, 5, 10, 10, 7, 17, 1, 2, 3, 4 and 2. So this is giving the answer 247, which is also not correct. So option C is the correct answer in that case. So in that way you can solve this problem also. Now moving to the next problem, what it says. Okay, in the next problem, in the broadband decoupled 13C spectrum, the number of signals appearing for the two pyrene diol A and B. So this is pyrene diol, this is also the pyrene diol, and you have to look for the carbon NMR spectrum for this one. and the options are given A, B, C, D, and you have to select the correct options. So this problem again is this problem is actually related to the stereochemistry or the symmetry elements present in the molecule. If you have the idea about the symmetry elements present in the molecule, only then you will be able to solve such kind of the problem. Otherwise it will be wild goose chase for you to solve such kind of the problem. But I am giving you the trick here. Whenever you have such kind of the problem, look for the plane of symmetry. Okay, if you don't know, if you are not able to understand the plane of symmetry, you can go for the CN axis present in the molecule. But I am giving you the idea by which you can easily solve such kind of the problem. So what I am doing here, this is the plane I am putting here, which is going in that manner. Basically it is your C2 axis. C2 axis means if you rotate this if you rotate this molecule from here to here by 180 degree, so this part actually, see, when you rotate this molecule this like that, okay, so what will happen, see, hold this handle and rotate this molecule, so this part will go up and this part will come up, and the resultant molecule which you will have will be indistinguishable from the A. That means the C2 axis is present in that case, right? When C2 axis is present, that means all the carbons which are present here would be exactly identical to the carbons which are present here. So one C2 axis is present here. Okay, so I can number those carbons here. Say this is my carbon number 1. When this is my carbon number 1, obviously this is also my carbon number 1, because they both are having this axis or this plane if you want, right? And now I am going for the next carbon. Say this is my carbon number 2. Obviously this would also be 2. Okay, now say this is my carbon number 3, which is reflecting here. This is also your carbon number 3. Similarly, on the same node, if you want, then this is carbon number 4, and this line is passing from here to here, so this carbon is also carbon number 4. Okay, now you have this. Then you can go further. Say then you can go you can come here. Say this is my carbon number 5, and this is reflecting here. This is also my carbon number 5. There is no problem in that. Okay, so this is how you can draw. Now you can go further like that. This is 6. This is also 6, right? If this is 6, this would also be 6. If this is 7, this would also be 7. But stop here, right? Please be stop here, because another C2 axis which is present in the molecule is passing through this, through the center, through this center actually. So again, if you rotate this molecule like that, this is your C2 axis. Okay, if you rotate molecule in that manner, so what will happen? This half will come here and this half will go there, and the reflecting image would be indistinguishable from the original one. So since this I have reflected here, so this and this, these two are same, there is no problem in that. Okay, these two are same. So what you can do, you can write 5 here. Okay, similarly if this is 5, this is also 5. If this is 2, this also be 2, and this is 2, this also be 2. Again I am giving you the thing. You have passed this plane from here to here, and you have been given carbon number 1 here, so this is also carbon number 1, because they are having the same planes. Okay, this is 2, this is also 2, this is 3, this is also 3, this is 4, this would also be 4. If this is 5, this would also be 5. If you identify another C2 axis present in it, so these two are reflecting through this, or you can understand, say this is the reflecting mirror plane here, so this is 5, this is also 5. Okay, when this is 5, this also be 5, this 5, this is also be 5, this is 2, this is also be 2, and when this is 2, this also be 2. So only 5 kinds of the carbons are there. That means this compound A will produce 5 signals. So check the options where compound A is giving the 5. In option A it is giving your 8 signals. So this cannot be your answer. In option B, compound A is giving 8 signals. This cannot be your answer. But in the option C it is giving 5. This can be your answer. In option D also it is giving 5. That means Now you have to select between the C and the D, which one is the correct answer. So the same thing you will apply on this particular molecule here. Then what I can do, I can say, I can pass this axis from here to here, like that. Say this is my C2 axis. That means if you hold the molecule and you rotate this molecule in that manner, this half after rotation will come here and this half will go there. Okay, and now you can look for the different kinds of the carbons present in it. Say for example, what I can do, say this is my carbon number 1. So this would also be my carbon number 1 because they are here actually. This is the carbon number 2, so this would also be my carbon number 2. This is my carbon number 3, this is also my carbon number 3. If this is carbon number 4, this is also my carbon number 4. There is no problem in that. If this is 5, then this would also be carbon number 5. If this is 6, then this carbon number is also 6. There is no problem in that. Okay, and this is your carbon number 7. There is no problem in that. Okay, and of course here also this is carbon number 8 and this is your carbon number 9. Okay, and this is your carbon number 10. So total 10 different kinds of the carbons are here in that case. Total 10 different carbons are there, because you see in that case you are having only this C2 axis. Don't confuse that. You can put the axis in that manner. If you draw the axis in that manner, then this OH and this and this, they will not actually give you the same result. So due to the presence of these two hydroxyl groups, these carbon 9, 8, 7 and 10, they are not same. But earlier case, C4 is similar to 4 due to presence of this, right? And 1 is similar to this due to presence of this. But this plane, this C2 axis is not here. So total 10 different carbons are there. That means your option D will produce 10 signals. So option A 5, option B 10, say 5, 10. So option C is in that case is the correct answer, and you can strike out this one. But this problem actually, such kind of the problem requires a lot of practice to solve actually. I hope this makes the sense. Now moving to the next problem, what it says. Okay, now this problem. An organic compound exhibited the following NMR spectrum. The compound among the choices given below. Okay, to solve such kind of the problem, what you can do, you can straight away look for some special results in that case. Okay, so I am solving one by one. This will take little time, but this will give you, this will clear your concept. Okay, right. Okay, just like that. This is carbonyl, this is double bond oxygen, this is this, and this is O, this is CH2, and this is CH3. Okay, say this is your structure, that is the structure A. So this is, since this is CH3, so what it will give you? It will give you the singlet, and this singlet would correspond to the 3 protons because CH3 is there. For these 3 hydrogens, I can write 3H, and since there is no nearby hydrogens on this particular carbon atom, so it is the unsplitted peak, it's a 3 proton singlet. Okay, there is no problem in that. Then again you can go here, this is CH2, so it's a 2 proton signal, but it would be a quadrate, Q. Why it is a quadrate? Because in this in the neighboring carbon you are having 3 hydrogens. So if you apply the rule n plus 1, that is 3 plus 1, that will give you the 4. So it's a quadrate. See, in the NMR spectroscopy, I already told you the first order spectra actually are solved by the n plus 1 rule, where n is the number of neighboring proton. So in that case, if you are looking for the signal for this one, of course 2H, and the signal of this one would be splitted by the 3 hydrogens. So how you can write? 3 plus 1, that is the 4, which is the quadrate. Okay, that's why I have written here 2 proton quadrate. Now looking for this one. So it's a 3 proton signal. It's 3 proton signal. Why? Because 3 hydrogens are there. and in the neighbor you are having the 2 hydrogens. So for 2 you can write 2 plus 1 equals to 3. So it's a triplet. 3 means triplet. So this is the result actually, right? Now you can check whether these data is given here, given in the question or not, right? So in the question itself, what is given? See, I am not looking for the signal at the 7 ppm. I am looking for the lower signal. Here you see 2 proton quadrate. Whether I am getting the 2 proton quadrate? Yes, 2 proton quadrate I am getting here. And 3 proton singlet. So I am getting the 3 proton singlet. Yes. And after that 3 proton triplet. Whether I am getting the 3 proton triplet? Yes, I am getting the 3 proton triplet. So this is also correct. Okay. Now I can go for your next problem. For your next problem, I can check your another answers. So up to now, it is looking like that my option A is correct answer, right? So I can write, I can mark this as correct one. Now I am going for the second one. For B, I can check whether B is correct or not. So how I can go for the B? This is my benzene ring. There is no problem in that. This is the carbonyl group, and this is my CH3, and of course this is CH2. Okay. And this is my O, this is CH2, this is CH3. Okay. So here in that case you see, for this one I can get 3 proton triplet. Why triplet? Because in the neighbor you are having 2 hydrogens. Okay, 2 plus 1 3, so it's a 3 proton triplet. And for this one, if you go for this one, so I can get 2 proton quadrate. Why 2 proton quadrate? Because in the neighbor 3 hydrogens are there. 3 plus 1 will give you the 4, so 3 proton quadrate. And for this I have already solved. For this one. So this will give you 2 proton quadrate. Okay. And this will give you the 3 proton triplet. But you see here in the question itself, I must have a singlet which is corresponding to the 3 proton singlet at 2.4 ppm. So chemical shifts are not very important here. 3 proton singlet I must have according to the question. But this question cannot give you the singlet because this CH3 is bonded with the CH2. This CH3 is also bonded with the 2. That means B cannot be your answer. So you can strike out your B. Okay. And now what I can do, I can remove this one because I have solved this. So up to now A is looking promising, but B is not the very good idea. Now for the next one, you see here, I am going for the option C. Say this is my carbonyl, this is CH2, this is CH2 again, this is CH3, okay, and this is my OH. So if you solve this, so for this one I can get 3 proton triplet. Why 3 proton triplet? Because 3 hydrogens are there for 3, and neighboring carbon is having 2 hydrogens, so 2 plus 1 will give you the 3. 3 means triplet. Okay. Now what I can do, I can check for this one what it will give you. So it will give you 2 proton multiplet. It will give you the multiplet. Why multiplet? See, you can see here in the neighbor 2 hydrogens are there, and in this neighbor on the right hand side you are having 3 hydrogens. So 3 2 plus 5, 5 plus 1 6 it can give you the sextate, which is kind of a multiplet. Okay. And if you go for this one, okay, so what it will give you? It will again give you 2 proton triplet. Okay. However, this will give you the singlet, but that singlet would correspond to the 1 hydrogen only because 1 hydrogen is there. But in the question itself given here, 3 proton singlet I must have, which is not there in the option C. So I can strike out my option C also. Okay. So I can remove this also. Now I am going for my next or last option, which is given here, which is this one. This is O, this is CH3, there is no problem, and then you are having this is O, this is ET, last one. So this problem actually, you see this option which is the option D, actually it is not O here. So it's a mistake here, guys. It is not O. Please remember, it is not O. This is a mistake here. Short mistake here, because I have seen this problem many times. So there is no oxygen here. Okay. So what you can do, you can erase it from here, and then you can write CH2 CH3, just like that. Okay. So of course this will give you the 3 proton singlet, very well, going with the options. It will give you the 2 proton quartet, again very well with the options. It will give you the 3 proton triplet, again very well with the options. And of course if you want to look the hydrogen signals, so this is these are the hydrogens here, these are the hydrogens here, which are the symmetry equivalent. So this and this hydrogens are equivalent, this hydrogen and this hydrogen are equivalent. Okay. On the same ground, in the option A also, this is the hydrogen, this is the hydrogen, this is another hydrogen, this is another hydrogen. So this and this are equivalent, this and this are equivalent. Okay. But you see now your option D can also be, it could also be the correct answer. But you can focus on the chemical shift, right? So chemical shifts are very important in that case. So you can look for the 2 proton quartet. This is my 2 proton quartet. So in the option you see, this is my 2 proton quartet, which is having the chemical shift of 4.10. And here for example I can write 4.10, and for this also I can write 4.10. So not for this one, 4.10. But please remember, this CH2 is connected with the electronegative oxygen, and due to this electronegativity, this is highly deshielded. When it is deshielded, the signal must be downfield, and downfield signal is away from the should be away from the TMS, and it is away from the TMS, right? 4.10. But in this option D, you can see this CH2 is connected with the hydrocarbon part here, and also here with the hydrocarbon part. So it is not that deshielded. Okay, this CH2 is not that deshielded. So it can never actually have the chemical shift around 4.10 ppm. It should be downfield somewhere around 1.5 ppm. Okay, so this option D can also be strike out. So option D is also wrong. So correct answer is your option A. So this is how you can solve such kind of the problems. Now moving to the next problem, what it says. Okay, my next problem says that an organic compound having the molecular formula of this, which is not actually very clearly written here. I'm sorry for that, but I remember it is C10H14. Okay, it is C10H14, and this C10H14 exhibited 2 singlets in the NMR spectrum. That means you are having only 2 singlets. So what would be the 2 singlets in the proton NMR and 3 signals in the carbon NMR? So I can write the data here. 2 singlets, and these 2 singlets are in 1H NMR spectrum, and then 3 signals. Since in the carbon NMR spectroscopy there is no chance of the signal splitting, so I can write signals only, regardless your doublet, triplet, right? This is doublet, triplet and multiplicity is not there in the carbon NMR spectrum. So 13C I can write here. So which is the correct option in that case? So again this problem will take the little bit of time, but I can solve the question here. Say this is my option A. Okay, this is methyl, this is also methyl, this is also methyl, this is also methyl. Now this question is actually looking quite good here. So this question is quite straightforward. You see, this is the plane of symmetry or the sigma plane. I can write sigma plane here. Okay, and if sigma plane, one sigma plane is there, then you see the another sigma plane. See, benzene is highly symmetrical molecule, guys. Please remember, this is another sigma plane. Okay, so due to the presence of this sigma plane, say this is carbon number 1. So this is also carbon number of 1, because these two are reflecting by this vertical mirror plane present in the molecule. And this is the horizontal plane, guys. This is the horizontal plane. So if this is 1, this would also be 1. So I can write 1 here, right? And this is also carbon number 1. There is no problem in that. Okay. So that means whatever the hydrogens are present here in the form of the CH3, here also in the form of the CH3, here also in the form of the CH3, they all will give you the one signal. Okay. So here 4 signals, or not 4 actually, 4, I can erase it. 4 methyls will give you one signal. There is no problem in that. In the carbon NMR, please remember, in the hydrogen NMR. Okay, and then you are having the next hydrogen. You see, one hydrogen is attached here and another hydrogen is attached here. Okay, so this hydrogen and this hydrogen, they are again equivalent. Okay, if they are equivalent, so they will give you the one more signal. So it will give you one signal here, one signal for the benzene hydrogen. So in total you are having the 2 signals. So this is the option here. You see here in the proton NMR spectrum, it will give you the 2 singlets. So this will give you the singlet because there is no splitting in that case. Okay, because no nearby hydrogens are there. And for this hydrogen also, these 2 hydrogens are equivalent and they cannot split each other because they are very far distance away from each other. Okay, and furthermore there is no neighboring hydrogens are there, so this will also give you the singlet. So this option, see, proton NMR is going well for this one. Right, now I can go for the carbon NMR. So in the carbon NMR also, you see, this is my plane of symmetry, that is the sigma plane. This is my another carbon, which is the sigma plane. Now if this is 1, this is also 1, and if this is 1, this is also 1, this is also 1. So 4 carbons are of same kind. Now this is the carbon 2, so this would also be carbon 2. This is carbon 3, this would also be the carbon 3. So this will give you the 3 signals. Please remember, again, if you know this, if you have the symmetry idea, then you will very easily solve this problem. So this is 2, this is 2. See, this one and this 2 cannot be same because this hydrogen is surrounded with this carbon, but this carbon is surrounded with the 2 carbons. So these 2 are, this and this different. Similarly, these and these 2 different. Okay, so one for this one, another for this one, and this is the symmetry plane. Just like that, this is the symmetry plane. So if this is 2, so this in the question itself, this would also be carbon number 2, this would also be carbon number 2. Okay, so in that case, you see how many signals you are getting? One signal for the 4 carbons which are present on the methyl form, and one signal for these carbons which I marked as 2, and one signal for this carbon which I marked as 3. So 3 signals you will get here. So option A is actually looking the correct option, right? So please remember. So if you have little bit of confusion, so I can draw it again. This was the case actually. Okay, this is methyl, this is methyl, this is methyl, this is methyl. I can write CH3 here, I can write CH3 here, I can write CH3 here, I can write CH3 here. Okay, and this is my sigma plane and this is another my sigma plane. So this is equivalent to this one because they are related by this symmetry, sigma plane, and this sigma plane is these 2 methyls are related by or reflected by this sigma plane. So this and this, this and this, they are also same. So these 4 methyls are of same kind. Okay, and say this is carbon number 2, this is carbon number 2 because this is reflected by this one, and this you see this plane is also there. So if this is 2, this would also be 2, this is 2, this would also be 2. So I can write 2 here. Okay, and this is your third carbon, this is your third carbon, because they are actually present on the this sigma plane. So 3 different carbons are there, those 3 carbon signals are there, 3 carbon signals. So straight away I can conclude that my option A is the correct option. So since the length of the video is going too much, so what you can do, you can practice for this B, C and D, and you will find that these cannot be answered, right? This will take too much of time, I am not going to solve this one. So option A is looking the correct option. You can solve by your own, and if you don't find the way how to understand the problem, you can comment in the comment section, I will reply. Okay, but right now you can understand the problem in that manner. Now moving to the next question, what it says. Okay, my next question, okay, again it's a very simple problem, and again it is based on the basic NMR spectroscopy principle. And what the question says, you have been given a gyromagnetic ratio for the proton, that is 2.7 into 10 to the power 8 Tesla inverse and second inverse. The resonance frequency of a proton in the magnetic field of 12.6 Tesla. Okay, so magnetic field is given in the Tesla here, and gamma is also given here, and you have to calculate the magnetic field strength. Okay, that means the resonance frequency for the hydrogen. So again it's a very simple problem, guys, there is no problem in that. Say this is the resonance frequency nu, and this nu is related by the gyromagnetic ratio divided by 2 multiplied by pi, and the whole thing is multiplied by the magnetic field strength. Okay, the value of the gamma is given 2.7 into 10 raised to the power 8 Tesla inverse second inverse, which is nothing but hertz, divided by 2 into pi, that means 2 into 3.14, which is the value of the pi, and whole thing is multiplied by the strength of the magnetic field, which is 2.6 Tesla, right? So this Tesla inverse and Tesla would get cancel out. Okay, and if you solve this value, so it would be 2.7 divided by 6.28, I hope. This is 10 raised to the power 8. Whole thing is again multiplied by 2.6, and of course the answer would be in the second inverse. So if you solve this again, this will give you 5.41 into 10 raised to the power 8 hertz. It simply means 541 multiplied by 10 raised to the power 6 hertz, and you know 1 megahertz equals to 10 raised to the power 6 hertz. Okay, so this you can write 541 megahertz, and this 541 is closely related to the 540. So option C is the correct answer in that case. You can easily strike out other options. The one thing actually which the new students of the NMR spectroscopy can think in the questions, how many times we obviously see many of the number of times we see that numerically when we have calculated the value, it is not exactly matches the value of the value given in the options. Remember, nothing is absolute in the NMR. In the NMR spectroscopy, all things are related or relative to each other. So it is very hard to get the exact value. You have to go for the closest value to solve the such kind of the problems. I hope this makes the sense. Now moving to the next problem, what it says. Okay, this problem is again looking like a very hefty one. So how we can go for this one? Very good. An organic compound C10H10O2, okay, this is the molecular formula is given here, which does not change the color on the ferric chloride solution. Okay, that means whatever the functional groups are there, they will not react with the ferric chloride. And you know the ferric, what is the test for the FeCl3 test actually. I am not going to the chemistry of the FeCl3 test, because for me actually the NMR data is sufficient to such kind of the problem. And the NMR data is given here, 7.3, signal at 7.3, signal at 7.0, signal at 6.9, 6.9 again, and 5.3, and 4.6. So the signals which are actually near to the 7 ppm, they all are related to the benzene signal. Okay, and this is the 1HBr, BR for broad signal. And remember, in the NMR spectroscopy, whenever you observe a signal which is the broad, it is always the exchangeable proton, which is the proton which is present in the system and gets rapidly exchanged with the solvent. So D2O is the solvent here, and with this solvent actually hydrogen can exchange, which actually broaden the signal. This 4.6 is actually it's a singlet. It's a kind of the the de-shielded group. At 3.9, again all are the de-shielded one. So first of all, we have to look for the options what are given here. See, 2 oxygens are given here. So whenever you have that 2 oxygen here, so you can go for the options where you can find some discrepancy. Okay, so you can look for this one. So I am going for this A. Okay. So for this A, this A cannot be answer. This A cannot be your answer. Okay. Why this A, for this, why we cannot have actually why we cannot have this answer? For this this is CH3 basically, no, and that means it will give you the 3 proton singlet. Okay, there is no problem with that. And this is your again CH3, so it will again give you the 3 proton singlet. So in the NMR data, I must have the 2 3 proton singlet. I can check whether I have the 3 2 proton singlet. So it's a 1 proton triplet, it's a 1 proton doublet, it's a 1 proton singlet, it's a 1 proton doublet, it's a 1 proton singlet, it's a 2 proton singlet, right? And it's a 3 proton singlet. So I am having the singlet here, I am also having the singlet here, but in the question 2 proton singlet and 3 proton singlet are there, but in this structure this CH3 is there, so it must be a 3 proton singlet. It is also CH3, it must be a 3 proton singlet. So this A cannot be your answer, because in the question itself only one 3 proton singlet is there, so you can very easily strike out this option A. So you can forget about this one. Okay, and now what you can do, we can go for another one. So say for example, and now I am going for C. Intentionally I am going to solve this C actually. So we can check whether this C is my answer or not actually, right? For this C actually, what you can have here, let me check whether it is the correct answer or not. Let me check. Okay, fine. Say this is the symmetry present here, and this is the symmetry present here. So what can happen? This hydrogen is here, and this hydrogen is here, and another hydrogen is there, and another hydrogen is there. Okay, so this hydrogen and this hydrogen, they are the same kind of the hydrogen. So that means you can have a signal regarding this one, and you can have the signal regarding this OH also. So 1 proton singlet, and of course this 1 proton singlet is there. So this is matching with the answer. Okay, and in that case, you see in the question itself, you see here, right? So 1 proton singlet, fine, it is 1 proton singlet, but this hydrogen actually would be splitted by this hydrogen. So this would be a doublet here, and this is again, if you see this one, this can be splitted by this one. So this cannot be your answer, because you see here 1 proton singlet is matching. At 4.6 you must have the 2 proton singlet. So this cannot be a 2 proton singlet. Why? Because this CH2 would be splitted by this one. So 2 proton singlet I cannot get for this species, and in the question itself 2 proton singlet is there. So based on this parameter, 2 proton singlet, which is given in the question, is not possible for this molecule. So I can discard C also. Now going for the option D, right? And this option D, okay, this OMe. So this is actually your 2 proton singlet. It is a 2 proton singlet. Let me check whether 2 proton singlet is there in the option or not. 2 proton, yes, it is a 2 proton singlet, right? So this is somewhere around 4.6 ppm. But remember, you see, this OMe is there and this OH is there, and if you follow the order, the inductive effect order, right, and in the inductive effect order, actually this OMe is having more minus I effect than the OH. So it cannot resonate somewhere around at 4.6 ppm. It resonate greater than 5. So the chemical shift, due to the presence of this OMe, the chemical shift of this group actually must be greater than 5.0 ppm. Why? Because this OMe is actually having the higher inductive effect. So this option can also be discarded from here. So what you left with the option B, which is looking the correct one. However, this option B and option D, they are very closely related, but based on the chemical shift value, say this is CH2, this should be somewhere around 5 ppm, but this is OH, which is CH2 is here, so it will always give you the signal, right? And this will give you the signal, since this proton is actually what you see here. This is 2 proton singlet I am saying. So this is exchangeable proton. It is given in the question. It is exchangeable proton. So it cannot split the signal actually, right? So this CH2, but this OH is having the lower minus I effect. So this value actually is more related to 4.6 value. Okay guys, so this is my next problem. Probably this is the last problem from the 2013 examination. And for methyl 4-oxo, this is methyl dash 4-oxopentanoate. I can draw the structure for this one. How I can draw the structure? Say this is CH3, this is my carbonyl. This should be connected with the CH2, this should be connected with the CH2, this should be like that, COOMe. Let me check. This is carbon 1, this is carbon 2, this is carbon 3, this is carbon 4, this is carbon 5. At 4 position you are having the carbonyl substitution, that is 4-oxo. Methyl is there for this, and 5 carbons are there, and it's a ester moiety, so it's a pentamate. Okay, the structure is fine. Now we have to select the correct chemical shift given here. Okay, so please remember, for ketones, if you have the ketones like that, for ketones you are having the chemical shift range somewhere around 205 to 220 ppm. Okay, for ketone. That means for C1. Clear? So what options actually we can strike out in that case? So before strike out the options, we can check another things, like if you have the carbonyl, okay, and if this carbonyl belongs to the esters, I can write ester here. So this will have the high field signal 117 to 185 ppm. Why this happens? You see, this lone pair is there, this will come here. Okay, that means this carbon is highly shielded, and when the carbon is shielded, the signal would be upfield. Upfield means high. See, in the chemical shift scale, it is more near to the your TMS signal. So 205 is downfield, and this 170 compared to this 205, it is the upfield signal. Okay, so let me check the carbonyl frequency, right? So carbonyl frequency for ketone. For ketone, that means carbon number 4, I must have the value somewhere around 205 ppm. Okay, I must have this value. So let me check whether it is there or not. In option A, it is C4. Let me check the C4. This is my C4. Okay, and this C4 is 172, so you can strike out this one. Now going for the option B, this is again, you see, option B again, it is 172. This cannot be your answer. You can strike out this also. Option C, yes, this can be your answer because 208 is close to this one, 208 close to this one. So out of C and D, we have to select the correct option. Now you can go for this OME, right? This methyl actually, this methyl is more close to the oxygen, so it must be downfield. It must be downfield. Okay, whatever the data is given in the question, you have to select the downfield shift. That means for methyl, that is OME. So in that case, you see here, this OME is 32. Okay, we have strike out this option already, but on the basis of the OME also we can strike out this one. This OME, this could be the correct for the OME, but for this it is not correct. This OME is 32, which is upfield when compared to the 51, so you can strike out C also. So option D is looking correct answer in that case. Now you see here how option D is correct. So this is OME. For this you will have the 51 ppm, which is the downfield signal when compared to the 32 ppm. For the ester actually, right, that is the C1. C1 must have the value in the range of this 170 to 185, C1. So for C1 you see it is 172, quite good. Okay, and then C4 again it is quite good. And then where is the C5? C5 is this one, this is 100, this is at 32. So based on your see, in that case what you can do, you can look for this OME signal, you can look for this signal and this signal. This will give you the correct option. This is the electron withdrawing group, right? This C, the carbon double bond oxygen, is the electron withdrawing group. So this this should be downfield signal. This CH3, that means C5 must be downfield. And you see here in that case, this C5 actually is around somewhere. However, this will not give you the correct idea. You can go for the C4 and you can go for the ester carbonyl and you can go for the OME. Okay. So based on this, you can see my option D is actually looking the correct option. So this is how you can solve the spectroscopy problem, but you need to practice a lot before going into the examination. I hope you understood the lecture completely. Okay, so that's it for today. Meet you in the next class. Thank you.